So in this lecture, let us talk about a digital signal. A digital signal is obtained from an analog signal by sampling. So let me denote the analog signal by x suffix a of t, and here the suffix a indicates analog, and this analog signal is sampled by the sampler. So you take x suffix a of t and give it to the sampler. Okay, so after the sampling you get a signal which is called x suffix a of n t suffix s. So you the switch closes periodically with the interval of t suffix s seconds. Here this s indicates sampling time or sampling interval, and t indicates time, capital time. Okay, and this sampling, or simply you can say t instead of calling ts, let me call t alone, not an issue. Okay, so this t is related to the frequency as 1 over s suffix s. Okay, now this is not a digital signal, it is a sampled version of analog signal. Okay, so this x suffix a of nt is called analog discrete time signal. Analog discrete time signal, because the time is discretized. Okay, so x suffix a of nt, so that is a notation. Okay, now this x suffix a of nt exists only at capital T, 2 capital 2t, capital 3t, and so on so forth, right? So it exists, you substitute n equals 1, so you will get x of t comma x suffix a of 2t, then x suffix a of 3t, and so on so forth. But its amplitude can be continuum, only time is discretized, that's it. Okay, now then what you do is you feed the signal into an A to D converter. Okay, give it to A to D converter, analog to digital converter, and what you get at the output is a truly digital signal, and that truly digital signal we are going to denote it by x of n, that's it. So originally we started with the analog signal x suffix a of t. You do the sampling, this process is sampling. After sampling you will get a discretized in time signal. So again you will get analog signal, but the time is discrete. So it is called this is called analog discrete time signal, and then pass it to A to D converter, and the output of the A to D converter is a digital signal, and the digital signal is denoted by a symbol x of n. Okay, if we give you a symbol of x of n, so this is a typical operation. Here the subscript a is lost in this, here there is no subscript because it has become digital. Okay, and in this process capital T is lost. Why? Lost in the sense that when small n becomes a variable. Okay, see, let me use a highlighter here. If you look at here, there is a n and ts, right? N and t, and here you have only n and t is lost. Okay, and the small n can take integer values. It takes integer values 1, 2, 3, and so on so forth, and it can take positive value or negative integer value, and each integer value in the corresponding discrete time signal corresponds to the integer multiplied by the sampling interval. What is capital T here? As I said, T is the sampling interval. So capital T is lost at the output of A to D converter. Okay, so capital T is lost in the digital signal. Why? See, if the signal was derived from an analog signal, then capital T has to be kept in mind. So how do you interpret then x of n and x suffix a of nt? Let me draw the diagram one more time to get more clarity. Originally you started with x suffix a of t analog signal. You do the sampling with the sampling interval of t. Then you'll get x suffix a of ent, and then you pass it through a to d converter, and here you are getting x of n. Now this t is lost, there is no t. Then how do you interpret this? So one way of interpreting this x of n is that capital T has been normalized to 1 second. Okay, let's say capital T is equal to 1. It can be 1 second, or it can be 1 millisecond, or it can be 1 microsecond, or 1 nanosecond, or whatever it is. Okay, so it is normalized. So let's take T is equal to 1. So in that case, what will happen? This T will disappear and only N appears here. So generally, when we talk about digital signals, in that notation, we will not carry this T all the way. Okay, we will simply ignore it and we will assume that T is equal to 1. Okay, so capital T has been normalized to 1. However, it is a beauty of DSP and discrete time signal processing that the mathematical techniques for handling discrete time signals and digital signals are the same. Okay, so whatever the techniques you have, the techniques can be used to analyze discrete signal as well as discrete time signal. Same technique can be used. So here you call it digital signal processing. And here you call it discrete time signal processing. Okay, and this one you call it in short form DTSP, discrete time signal processing, and here DSP. Okay, so whatever the transforms, formulas, techniques, all are equally valid for this guy and this guy. No need to develop any separate thing for DTSP. So that is the beauty of this DSP course. So you can use a Z transform for DSP as well as DTSP, no issues. Okay, so both are explained in the same way, both are analyzed by the same way. Okay, so you use difference equations. Therefore, for both DTSP and DSP, you can use difference equations. And you can use discrete time Fourier transforms and so on and so forth. Okay, so whether the dependent variable is a continuum like xa of nt or a discrete amplitude like x of n. See here the amplitude is discrete. Let me write down one more, this very very important point, subtle point we need to understand. Subtle points. Okay, so you have xa of t. Here time is continuous and amplitude also continuous. Once you do the sampling, you will get a x suffix a of nt, and here time is discrete and amplitude is continuum. And if you take x of n, in this case time and amplitude both are discrete. So even though the amplitude is continuous in this case, both are analyzed by the same technique. Okay, that's it. And therefore we will use x suffix a of nt or x of n interchangeably, no difference. Okay, we will always take that the signal has been discretized in time as well as amplitude. Okay, in digital signal processing course, we always assume that the time is discretized as well as amplitude also discretized. Okay, and the next point is about the capital T. This capital T is called a sampling interval. Sampling interval. And obviously the sampling interval is reciprocal of the sampling frequency. So that sampling frequency T suffix S is called 1 over T, and this is called a sampling frequency. So how many samples per second you are taking, that is called a sampling frequency. Here the suffix S indicates sampling. So this is the symbol that we will use for the sampling frequency, and as we will see later, our signal processing must be limited to half of the sampling frequency. You can't go beyond that. Okay, so the sampling frequency must be half of the sampling frequency must be twice the highest frequency component present in the signal. Okay, that we will discuss a little later. Okay, when I say my sampling frequency is 8000 samples per second, 8000 samples per second, then my frequency content, frequency in the analog signal must not exceed 1/2 of the or half of the Fs. That means what? It should not exceed 4000 Hz. So this is called a Nyquist criteria. So we will discuss this little later, no problem. Okay. So the highest frequency content in the analog signal is related to the sampling frequency. For example, you take mic, and here you will get voice signal, and let's say the voice is from 0 to 4000 Hz. So what you do is just to 2 times of this maximum frequency. See, this is my minimum frequency, and this is the maximum frequency content present in my voice. So I should take the maximum frequency, multiply by 2. So that is called Nyquist criteria. Let me call this is F min, and this is F suffix maximum. My sampling frequency Fs must be greater than or equal to 2 times of F maximum. So if you do the sampling in this way, then you can reconstruct the signal without any distortion. So this is called a Nyquist criteria. Nyquist. Criterion. Criteria is plural, right? Criterion. Okay. So now finally we got digital signal. When I say digital signal, both time and amplitude are discretized. And this x of n, what is x of n? It is a sequence of numbers. Okay, what is x of n? It is a sequence of numbers. Let's say, how do I say it is a sequence of numbers? Let's say you have a signal like this, and you take one sample here, and let's say maybe I will draw the diagram neatly so that you can understand clearly. The signal is like this. You take one sample, let's say this is 2 volts and this is 4 volt, and this point is, let me elaborate, this point is rounded off to this value, so therefore this is 4. You take another sample, this point, again this is rounded off to this value, so again this is 4. You take another sample here, and this is rounded off to this value corresponds to 2. And you take one sample here, so this is rounded to this point, So this again 4. You take one more sample, and here let's say this point is 6 and this 6. Okay, so here this is 1 microsecond, or let's say 1 millisecond, 2 milliseconds, 3 milliseconds, and so on. Maybe, I'm sorry, this point I took wrongly. Let's say this is somewhere, okay, like that. So in between the gap is t is equal to 1 millisecond. And what is your sampling frequency? Sampling frequency is 1 by 1 millisecond. It is 1000 samples per second. And it's a sequence of number. Why is it sequence of number? See, x of 1 is equal to 4, and this is 2. So x of 2 is equal to 4, x of 3 is equal to 2, right? X of 4 is equal to 6, and so on and so forth. So finally you'll get 4, 4, 2, 6, right? So this is my x of n. Therefore x of n is a sequence of numbers. Once you do the sampling of a given analog signal, then you'll get a sequence of numbers. And this sequence is sometimes, is simply represented as x of n. Okay, where this n takes values theoretically from minus infinity to plus infinity. Okay, but the intervals of 1. That means what? Let's say you start from 10,000 minus 10,000. The next point will be minus 9,999, right? And then minus 9,998, and so on and so forth. Okay, or to show that it is a sequence, we sometimes give the symbol of x of n with the curly brackets like this. Okay, for example, we can have a signal like let's say minus 1, 0, 1, 2, minus 2, and so on and so forth. So how do you represent the signal? You can put it in the curly braces, dot dot dot. It comes from somewhere, we don't know. Minus 1, 0, 1, 2, minus 2, and so on, like this. Okay, so I am writing it ordinary arithmetic, but I have taken them to be coded or quantized into integer numbers. See, here it is quantized to integer numbers. See, the exact value is this one. Exact value. What is the exact value? Let's say 4.2345, like this. But I quantized this 4.2345 to 4. Right? Let me write down this. 4.2345 is quantized or rounded off to what? 4. So this process is called quantization. Once you do this kind of quantization, then what will happen? There will be some error. That is called quantization error, or sometimes people call it noise. Now look at here. So in this sequence, I don't know where the n value will be denoted. Now what is the value of n here, and what is the value of n here, and what is the value of n here? So we don't know. Okay, so generally if you write a sequence like this, the 0th sample is denoted by an arrow. So what you do is you remove all these arrows, you put a simple arrow. Maybe I will use a different color. Okay, let me put arrow like this. So wherever you find the arrow, that arrow indicates 0th sample. So this arrow indicates n equals 0. Okay, so therefore it means that at n equals plus 1, the value will be 2. At n equals plus 2, the value is minus 2. At n equals minus 1, the value is 0. At n equals minus 1, the value is minus 1, and so on, so forth. Sorry, n equals minus 2. This one is at n equals minus 2, the value is minus 1. At n equals minus 1, the value is 0. n equals 0, the value is 1. At n equals 1, the value is 2. N equals 2, the value is minus 2, and so on and so forth. Okay, so this is the complete description and representation of the signal. And here we will not write binary numbers. For example, this 2 I can write as 0 0 1 0, and this 1 I can write as 0 0 0 like this, and this 0 0 1, and this 0 I can write as 0 0 0 0. These all are called a binary representation. But in general we will not use binary notation, we always use decimal numbers. Okay. So we will not, we will write the integer equivalent of the numbers. We will not write down the binary numbers here. And one more thing is, look at the sequence. The sequence is this real, right? This is real numbers. But the sequence is not necessarily real. It can be complex. Okay, the sequence can be complex, like you can have ... 1 plus j, comma 2 minus j2, comma like that. It can be a complex sequence, and so on and so forth. Okay, for example, if you want to derive an analytic signal, as you know, the analytic signal has a real part and an imaginary part, which simply means that these signals are orthogonal to each other. Okay, so imaginary part actually is also a real signal which is orthogonal to the real part, and therefore the signal can be real or complex. Now let us talk about length of the sequence. What is the length of the sequence? So this topic is very important. So the length of the sequence is the total number of samples in the given sequence. Let me write down total number of samples in the given sequence. That is called the length of the sequence. For example, if I take the previous exam, ... let's say -1 0 1 2 and -2 and ... Now in this you can't count, right? It starts from minus infinity and goes up to plus infinity. Okay, in the left hand side it goes up to minus infinity, and in the right hand side this goes to plus infinity. Then obviously it is an infinite signal, right? Doubly infinite. In the right side it goes up to infinity, in the left hand side also it goes infinity. So it goes to the left also, it goes to the infinity, to the right also. Therefore this sequence is called a doubly infinite sequence. Suppose we have a sequence simply like this. Let's say 1 2 3 -1 4 like this. Now there is no dot in the right hand side, there is no dot in the left hand side also. See here, no dots. And here also no dots. In this case it is a finite sequence length. Okay, finite length sequence. You can count how many how many points are there. I mean now how many number of samples are there in this. 1 2 3 4 5. So the sequence length is 5. Okay, so the length of a sequence is equal to the number of samples in the sequence. Therefore here the length is 5. That's it. Okay, let's say, let me put 2 1 4 5 7 9 like this. Now let me put the arrow mark like this. If I put arrow mark like this, then what happens? The sequence starts at n equals 0. So this is 0th sample, first sample, this one is second sample, and this guy is third sample, this guy is fourth sample, and this one is fifth sample. Therefore n takes the value from 0 to 5, right? But what about the capital N length of the sequence? 6. 1, 2, 3, 4, 5, 6. Okay, even though the small n ranges from small n goes up to 5, but the length of sequence is 6. That is total number of 6. So I have to include at 0 also. I have to count from 0 also. Therefore, n goes from 0 to capital N minus 1. So this is a general notation. Okay, therefore the small n lies between 0 and capital N minus 1. Okay, because there is sample at small n equals 0. Okay, now a sequence, if it exists from somewhere, okay, exists from some value of n, let's say n is equal to capital N1, and goes to the right up to any value that one likes, but on the left the sequence is all 0. Okay, so let's say this all are 0, it starts from infinity 0 0 like this. At one point, let's say n is equal to capital N1. I don't know, this N1 can be anything other than infinity. Okay, N1 can be 1 or 0 or minus 5 or whatever it is, and the sequences exist here like this. So the sequence exists to the right of n is equal to N1. On the left hand side, no values. The right hand side, yes, you have non-zero values. Okay, this n1 can be anything. N1 can be 0 or minus 1 or plus 10, whatever it is. Then the signal exists to the right only, and therefore it is called a right-sided signal, and RSS, right-sided signal. On the other hand, if the signal exists to the left of a point, let's say this point is N2, and it exists like this, So let's say n is equal to capital N2, and to the right side no signal up to infinity. Here also no values up to infinity, minus infinity. But the signal exists to the left of this value. Okay, this N2 can be anything, again as I said, 1 or 10 or minus 10 or whatever it is. So such a signal is called a left-sided signal, LSS. Okay, sometimes a signal can be a combination of left-sided and right-sided. Okay, provided it is what length? If it is a finite length, that you can always be with a right-sided and a left-sided signal. If it is infinite length, then obviously it is a combination of right-sided and left-sided signals. So a signal or a sequence can be even or odd, or a mixture of even and odd. A sequence can be even, odd, or a general signal. Okay, so the definition is very simple. Okay, let us talk about even signal. So a even sequence is the one whose left side is mirror image of the right side. For example, you consider the value at n equals 0, its value is 1, and 2, its value is 2, and 3, its value is minus 2. Okay, this is n. Take the mirror image of this. I'm sorry. Let's say this point is 1 and this point is 2. At minus 1, take the mirror image. So mirror image will be 2. And 2, you take the mirror image, the value is minus 2. Therefore, this is the even signal. Okay, simply you are taking the mirror image of the right side. Okay, it is an even signal. In other words, an even signal, it is denoted by x suffix e of n, is the same as x suffix e of minus n. Okay, that means what? X suffix e of 1 is the same as x suffix e of minus 1, right? X suffix e of 2 is the same as x suffix e of minus 2. So this is called an even signal. On the other hand, an odd signal is the one in which, let me denote by x suffix o of n, odd, is defined as the negative of the x suffix o of minus n. That's it. Okay, so in other words, it is like this. At n equals 0, you say the value is 0, let's say. At n equals 1, let's say this is 2, and n equals 3, let's say minus 2. What you do is, at n equals minus 1, it takes the minus of that value, and n equals minus 2, it takes plus 2. So now you should ask the question, what should be the value at n equals 0? Because the condition is x suffix odd of 0 must be equal to minus of x suffix 0 x suffix o of minus 0. Minus 0 is the same as 0, right? Minus x suffix 0 o of 0. This is o, okay, odd. The suffix o indicates odd. Okay, now no value will satisfy this condition. X o of 0 is the same as minus x o of 0. Which value will satisfy this condition? Only 0 satisfies. No other value satisfy. So by looking at the signal, simply you can tell us like whether the signal is odd signal or not. The value must be 0 in order to be a signal, an odd signal. Okay, therefore x suffix o of 0 must be equal to 0. An even signal can have any value at n equals 0, no issues. And the odd signal must have a 0 value at n equals 0. Okay, now in general, a signal is neither even nor odd, need not be even and need not be odd. But such a signal can be decomposed into two parts, an even part and an odd part. You can decompose into two parts. So you take a general signal. This is the general signal, and this general signal is neither even nor odd. Okay, but such a signal can be decomposed into odd part and even part. How do you decompose? So x of n is decomposed into even part, x suffix e of n plus x suffix o of n, and this is the even part and this one is the odd part. So in general, it is a combination of even and odd part. And if you want to find out the even part from the general signal x of n, it is very easy. Okay, so you just replace n by minus n. So x of minus n is equal to x suffix e of minus n plus x suffix o of minus n. Now we know the definition for even signal. X suffix e of minus 1 is the same as x suffix e of n, and this one is minus of x suffix o of what? N, and this side x of minus n. Let's call this is equation number 1 and this is equation number 2. Now add these two guys, 1 and 2. So x of n plus x of minus n is equal to 2 times x suffix e of n, and this odd part will be 0. Therefore from this, x suffix e of n is the same as, is equal to x of n plus x of minus n divided by 2. Similarly, you do the same algebra, but now you subtract 2 from 1, then you will get odd part of n. So this odd part of n directly I will write down the result, which is x of n minus x of minus n divided by 2. Okay, so in a similar manner the odd part is given by this formula. It's very simple to derive. Okay, so there are problems on the textbook by S.K. Mitra. You can work on it. Okay, many problems are there. So there are many problems on the book on decomposition of the signals into even and odd parts. So try to work out as many as you can. Very simple. Periodic sequence, or sometimes called periodic digital signals. Okay, a signal x of n, a digital signal. When I say x of n, it is a digital signal. X of n is said to be periodic if x of n is equal to x of n plus small k times capital N, where capital N is the positive integer. Oh, it can't be a negative. Okay, it must be positive integer, which means that x of n repeats after every capital N samples. Alright, this is called a periodic signal. And smallest capital N for the validity of this relation is called the period. This capital N is called a period. Smallest n is called a period. So why smallest n? I will tell you. Okay, and here the period therefore has no dimension. Okay, this n has no dimension. It is not in seconds or something else. Okay, don't confuse with the capital T in the analog signal. So it is not in seconds or not in microseconds. It is a pure number. It is a pure number. That is, it indicates the number of samples after which the sequence repeats. I think you know why this is a pure number. It is not it doesn't have any units, because once you do the sampling and normalize, the time parameter will disappear. Okay, it is a purely number and no dimension for this. Okay, it indicates the number of samples after which the sequence repeats. Okay, now the next question is, why is it a smallest capital N? Suppose let's say 20 is the period of a signal, then what will happen? This repetition will occur at every 40 or every 60 also, and so on and so forth, right? But the repetition will not occur for 10. No, it will not occur at 10. So the smallest value of n for which this relationship holds, or this relationship is valid, is called the period of the periodic signal or sequence. Okay, now we will show a little later that a cos omega t or a sin omega t is always periodic. Okay, it's a continuous time signal, but this statement is not true. About a cos omega not n, okay, or a sin omega not n. Okay, these two guys are not always periodic. Some cases it is yes and some cases no. We will show it. Okay, so we will show you a little later that this is not the case for discrete signals. Okay, then we will move on to what is called a bounded sequence. Okay, a sequence x of n such that the magnitude of x of n, whether x of n is real or complex, okay, positive or negative, is bounded, that is less than or equal to some number, capital M, okay, which is less than infinity. Bounded means less than infinity. Okay, so you take x of n for all values of n, you take the magnitude if it is a complex number. If it is real, no need to take magnitude, and this value is bounded to some value capital M, and this capital M is less than infinity. Less than infinity means what is the meaning of this mathematical notation? M less than infinity means it's a finite value, that's it. Finite value will be written in mathematics by m less than infinity, and this condition is true for all values of small n. Okay, so x of n, the magnitude of x of n, whether x of n is real or complex, positive or negative, that doesn't matter, it is bounded. That means what? Less than or equal to some number, and that some number is a finite number. So such a sequence is called a bounded sequence. Okay, next we will move on to absolutely summable sequence. Okay, so if the summation of the magnitude of x of n is bounded over its length, total length, you take x of n, sum them up. Okay, let's say n equals minus infinity plus infinity. This total summation is bounded to some number, let's say capital P, and this number is a finite number, so I put a less than infinity. Okay, so the summation is taken in general from minus infinity to plus infinity. It is bounded, then x of n is said to be an absolutely bounded sequence. Okay, and then we will move on to square summable sequence. Okay, so you can similarly define a square summable sequence. That means what? You take x of n, if it is complex, you take magnitude and then square them up. Okay, and then you take the summation from n equals minus infinity to plus infinity, and this square summable is less than or equal to some number, let's say q, and this is a finite number less than infinity. Okay, square summable sequence is one in which the magnitude is squared and then summed up from n equals minus infinity to plus infinity, and if this total summation is less than some number q, which is less than infinity, strictly less than infinity. Okay, here less than or equal to, and here strictly less than. Okay, don't forget that. Then the sequence x of n is called a square summable sequence. For example, suppose you have a sequence x of n is equal to 1 over n. Now the question is it absolutely summable? The answer is no. Why? Because you have 1 over 0 at n equals 0, right? What is 1 over 0? Infinity. So if it is infinity, then it is not square summable, right? Infinity square, it is not. See, what is x of 0? X of 0 is equal to 1 over 0. 1 over 0 is infinity. If you square this, then what will happen? Infinity square. So this is not a finite value. Therefore, this is not a absolutely summable sequence, this x of n. X of n is equal to 1 over n. Now, what is this formula? N equals minus infinity plus infinity, x of n square, and then less than or equal to q less than infinity. And you notice that this formula represents the energy of the signal. Recall this formula from your signals and systems course. Square of the amplitude. Okay, square of voltage with the 1 ohm resistance is the energy. Square of current with 1 ohm resistance is also energy. See, I square R. What is this? Energy. And let's say R is equal to 1 ohm. v square over r, this also again energy. So instead of v square I have modulus of x of n square. So in similarity with that, the energy of the sequence is defined as the magnitude of x of n squared summed up over all samples. So a square summable sequence can also be called alternately a finite energy sequence. Finite energy sequence. Okay. Square summable sequence is called finite energy sequence. Okay. A sequence may or may not be square summable. Okay, and then we'll talk about average power. So we have defined what is energy, and power is energy per unit time. Okay, so in similarity, what is power? Let me put average power. So this average power is equal to energy per unit time. In similarity with that, what we do is we find out the energy over a certain length. Okay, let's say we are talking about average power, right? So let's say we are going to find out the energy. First you take the x of n. If it is complex, then you take modulus and then square it and sum them up. Let's say n is equal to minus capital K1 to plus K1, or simply K, no need to put K1, okay. Simply put K, minus K2 plus K. And what is this? This is the energy of the signal. Okay, the energy over the length, how much? 2k plus 1, because one sample is sitting at n equals 0, that is why this 1 is coming. Suppose you have the sequence like this, minus 2, 2 plus 2, then what will happen? Minus 1 plus 1, there is one sample at n equals 0. So totally how many samples are there? 5 samples. So 2 times 2k plus 1, here k is equal to 2, therefore 2 times 2 plus 1, it is 5. So this 1 has to come, 2k plus 1 samples. Now what I am going to do is, I divide by its length. So what is the length? 2k plus 1. Then this whole formula will be, represent average power. Average power. Okay, over the same length. What is the length? 2k plus 1. And this one represents, let me use this color. This represents energy over the length of 2k plus 1. Maybe I'll write down neatly. Sigma n is equal to minus capital K2 plus capital K x of n, and this one is energy over the length. What is the length? 2k plus 1. Now you divide by 2k plus 1, and this whole thing is denoted by, the whole thing denotes average power over the length to k plus 1. So what we do is we allow capital K to go to to go to infinity. Then we have covered the total signal, that is total length of the signal. So you allow this L or K to go to infinity, 1 over 2k plus 1, then sum them up, x of n, and where n is equal to minus capital K2 plus k. So this one defines average power. Okay, and this is denoted capital P, average power of the signal. So it is a limiting process. Okay, you cannot go on adding up infinite length sequences. So what you do is you go to sufficiently large number, okay, increment by 1, 2, 3 and so on, and see does the average power change. Usually sequence trail off, okay. If you keep on add it, then the sequence will trail off at very large values of n. Okay, therefore this definition is a meaningful definition, okay, meaningful definition for the average power. Now, how about the periodic signal? How do you find out the average power? Suppose if you have a periodic signal, then how do you find the average power? If you have a periodic signal, then your job is very simple, okay. A periodic signal of period n, because it is going to repeat after every n samples, capital N samples, right? Then all you have to do is, you have to take the average over one period, that is enough. No need to take the average from minus infinity to plus infinity, since it is periodic, okay. Because every period is identical replica of any other period, and therefore what you do is, you take x of n, square of x of n, and then sum them up. Let's say n equals 0 to n minus 1 and divide by 1 by n, that is enough. Okay, because at n is equal to small n is equal to capital N, it starts repeating, and you divide by capital N, it will give you the average power of the periodic signal. Average power of the periodic signal. Okay, so we have defined absolutely summable sequence. So we have defined, so till now we have defined absolutely summable sequence, square summable sequence, which is the same as finite energy sequence, and then we defined the average power in a sequence. Okay, so I think let me stop at this point. In the next lecture we will talk about elementary signals. Okay, so we will look at some typical elementary signal or elementary digital signals. So let me stop at this point. Thank you very much.